Chapter 2, we're going to start with here, and we're going to cover all kinds of things, obviously, like measurements. We're talking about significant figures. We're going to talk about scientific notation. We'll talk about conversions, problem solving, dimensional analysis, which is the way they want you to learn how to do problems in chemistry. And we'll finish up talking about density. A reminder that these handouts can be found on our Canvas site. So if you want to use them, that's where you can go find them and download them. The kind of handouts to take notes on. Again, pretty much a lot of the stuff, or pretty much most of the stuff, will be on there, except for, again, sort of examples and stuff that we do here together. A reminder as well, I am recording, so that's what the microphone's for, so the computer will catch, obviously, my voice and all that good stuff. All right, so let's get into it then. So the first really sort of important thing about any type of measurement is really units. So if you say, hey, I got like 50, right? If I can get my zero to close there, 50. Really, what does that mean? 50, pennies is different than 50 jelly beans, much different than $50. So a number is, just a number. It really has no meaning unless there is units. So whenever you take measurements, you should always get into a habit. You should always have the correct number, the correct numerical value, and you should always have the proper units so people understand what you're talking about. So always a number and always a unit. Definitely in chemistry, those two things should always go together when you are taking them. Now in lab, a lot of the lab reports there kind of fill in the units for you, but as you continue on in chemistry, they will not do that for you. So you should always, again, get in the habit of writing those units with it. When we talk about units, there's really a couple of common systems. There's the English system, which is pretty much what we use here. Then pretty much everybody else uses the metric system. Obviously, that could cause a lot of problem. As you imagine, the world sort of gets smaller, everybody doing business with each other. So if everybody's using different sort of units, there really can be some major issues that can occur. So in 1960, they got together a conference on weights and measures. Sounds like fun. And they basically came up with a sort of universal unit for science, and we use a lot in chemistry. And sometimes we use the SI system of units. SI system of units is the International System of Units. For the most part, it's pretty much based off the metric system. So it's very much similar to the metric system. So you'll sometimes see a lot in chemistry, the SI unit for mass is this, or the SI unit for volume is this. And again, we oftentimes will use sort of these SI units. So here's are some common units for different quantities. You should be sort of familiar with some of these here. Mass is the kilogram. As we will see, we do use sort of variations of that. We use grams a lot, milligrams a lot, but kilograms sort of the standard unit. Length is the meter. Also, we do use very much different versions of it as well, like centimeters, millimeters, kilometers. The time is seconds, and temperature. You're familiar with a unit of temperature, which you might not be, which is Kelvin. And pretty much if it's chemistry and you're doing something with 0.8, usually will end up in that unit of Kelvin. Other sort of SI units, the amp or amperage is, for voltage is a common unit. But these are ones that we come across a lot of things of quantities of mass, length, time, and temperature. So let's talk a little bit about some common length type measurements that we come across. Like I mentioned before, the meter, definitely we do see a lot. The meter is about 39.37 inches. These sort of relationships here are ones we do come across a lot, and you should know 1 centimeter is basically 0.01 meters, or 1 times 10 to the minus 2 meters, which is a scientific notation. Centimeters and meters are converted a lot in chemistry. 1 decimeter is 0.1 meters. I would say another one that we see a lot is the kilometer to meter. Definitely conversion does come up a lot. So there are 1,000 meters, and 1 kilometer or 1,000 is 1 times 10 to the 3 meters, which is written in scientific notation. Now, because really the SI unit and a lot of what we deal with is sort of based off of the metric system, a lot of times in the metric system, we do sort of change the unit of the measurement by using prefixes. So we're not using really maybe big numbers a lot of times, or maybe really small numbers. So these are some different prefixes, and you definitely should be familiar with this table. I would say, and it is out of your book, I think you have pretty much this table. I would say everybody on this list, we do come across a lot in chemistry. Definitely in this class, centi, milli, kilo, we do see a lot. A little bit of micro and nano, but if you go on to 1A, you will definitely see micro and nano a lot in some calculations that you take. I'll be honest with you, mega occasionally, not really much in here, but in other classes. So these meanings do represent something, and very often when people use sort of a table like this, or when they remember a table like this, it's very common that they sort of do it incorrectly a lot. So for example, mega is 10 to the 6. By the way, that is like 1 times 10 to the 6 is what that meaning is, written in scientific notation, as we'll talk about in just a sec. For example, centi is 10 to the minus 2, which is basically the same thing as 0.01. So if you were going to say find a relationship, say between and you remember this list, or you look at this list, the relationship here is what we see here is how much there is in the base unit. So this is how much there is in the base unit. So when we talk about the base unit here, centimeters and meters, the base unit here is meters. So in 1 centimeter, there is 10 to the minus 2 meters. And it's very common. People will do it backwards. They'll say like 10 to the minus 2 centimeters is 1 meter. So it's always one of the prefix unit is how much of the base unit there is. So for example, if we had 1 kilometer and we look up kilo here, kilo is 10 to the 3, that would be 10 to the 3 meters. So that is the proper way to use that. And like I said, people always want to do it the opposite way around and go, there's 10 to the 3 kilometers in a meter. So again, that is the proper way to use that. Does it matter what the base unit is? It doesn't. So for example, if the base unit was a volume like liters, in 1 centiliter, there would be 10 to the minus 2 liters. In 1 kiloliter, there would be 10 to the 3 liters. So it really doesn't matter what the base unit is here. Obviously on the right there, the base unit would be liters, which is the volume. On the middle there, or to the left there, is meters. For example, milli is also one that we use a lot, which is 10 to the minus 3. And in 1 millimeter, there is 10 to the minus 3 meters. And 1 milliliter, there is 10 to the minus 3 liters in this case. So again, that is the proper way to sort of use that. Now, there is sometimes people like to kind of use maybe the bigger number versions of it. And by the way, how you get that, for example, is you divide 10 to the minus 3 to both sides. And that gives you that there is 1,000 milliliters in 1 liter, which is, again, basically the same conversion, just using the larger number. So in some cases, you know, that's really what this meaning is here. You can kind of divide it out. and the smaller unit will have sort of the bigger number. Any questions on that there? So you do need to know some of these, definitely the ones that are probably on this table, probably the other two as well. And again, you can use whichever meaning you want. You can use the kind of decimal form meaning of it, the relationship, and the power 10 relationship. Any questions on that? Now here's a comparison of English versus metric relationship. Inches being in the English sort of measurements, metric here being centimeters here. And this one for sure is one that you need to know, that there are in 1 inch, exactly 2.454 centimeters. That's an exact sort of conversion between them. By the way, this is a ruler, in case you're not familiar. So we have inches up on top. We have centimeters on the bottom. The small little dashes are what? And they are millimeters, yes. So these are millimeters, the small little dashes. There's 10 millimeters in a centimeter, yeah. So little guys on the bottom there are millimeters, bigger numbers are centimeters, and obviously up on top there are inches. Any questions on that there? So let's talk about some common units of volume. Volume is basically the amount of three-dimensional space that's occupied by a substance. The SI unit for volume is meters cubed. Here are a couple of important sort of conversions that you definitely should know, and that would be these guys here in the box. 1 decimeter cubed is equal to 1 liter. That's a good one to know, but I'll be honest with you, we don't really come across it all that much, but in here at least. But we definitely do come across the ones that we see here in the box. 1 cubic centimeter, which is what that is, centimeters to the 3rd power is a cubic centimeter, is equal to 1 milliliter. A milliliter and a cubic centimeter are basically a 1-to-1 conversion. So if you need to convert between the two, it basically just changes the unit. The number stays the same. Milliliters, a very, very common unit of volume that we use a lot in the laboratory. Most of our glassware is in milliliters, and those are very common sort of measurements that we do take. Definitely the 1,000 milliliters is 1 liter, is one that you use like nonstop throughout chemistry. You need to know that one as well. So you may be asking, how do you get a cubic centimeter? A couple of things about a cubic centimeter, and another version of a cubic centimeter is a cc, is sometimes used. Cc stands for cubic centimeters. You hear it like in the medical shows, right? Give the guy 5 cc's of this before he croaks, right? So that's basically 5 milliliters. And again, these are all equal to 1 milliliter. Now, when we have a unit of centimeters by itself, that is a length measurement. It is not a volume measurement. But if we have something like a cube, we could actually take 3 different measurements. We could take a measurement of the length times the width times the height. And since each of these things are all length measurements, we could take them in centimeters. So that would be centimeters times centimeters times centimeters, which gives us a cubic centimeter, which is a volume. So a very common way that we could find the volume of, say, like a cube or something like that, is to basically take 3 different length measurements, multiply them together, and that would be cubic centimeters, which would be the volume of that cube. That's also why here we see a decimeter cubed is equal to a liter. Again, that would be 3 different sort of length measurements multiplied together, which becomes a volume. Any questions on that there? All right. Now let's talk a little bit about mass. Mass is the quantity of matter that is present in an object. Matter is basically anything that occupies space and has mass. The fundamental unit of mass is a kilogram. And again, some very common units of mass that we come across a lot here that you do need to know. This one right here is a good one. 1,000 grams in a kilogram. That is something that we see a lot. Also milligrams. There's 0.001 grams in a milligram. Are the milligram and the milliliter, they're the same sort of deal. We saw earlier that there was 1,000 milliliters in a liter. There would be 1,000 milligrams in a gram. So it kind of works the same way. Again, those conversions, yeah. Why is it? Say again? The gram is just honestly, it's kind of what they chose. So a lot of metrics type measurements are done in kilograms. So if you ever gone to like the doctor, you probably have, right? So sometimes they'll also record your weight in like kilograms and stuff like that. So it's a very common metric unit that was just sort of chosen. Again, it kind of makes some of the larger units of grams a smaller unit, sort of more manageable unit for everyday use. And rather than having say like, this guy's like 2,000 kilograms or something like that, or 2,000 grams, it's like two grams and stuff like that, kilograms. Yeah. We will. So we'll get into that a little bit later on. Yeah. Other questions? Okay. So obviously when we do use mass here, or sort of get the mass of an object, we do use this. This is what is referred to as a balance. We're going to use it today, obviously in lab. A balance is a fancy word for a scale. And obviously we put things on there. To get the mass of the object, we obviously use a process known as tearing it to zero it out before we do there. Now, there is a difference, technically speaking, between two words that are sometimes used interchangeably, which is mass and weight. And the difference between it is weight does take into account the force of gravity on an object, where mass is sort of independent of the force of gravity. That's why your weight here and say that your weight on the moon would be different, 1/6 of what you would do here. But your mass would be the same. So it's really important in chemistry when you do weigh something that you actually refer to it as the mass of the object. That is typically what we refer to it as, and not the weight of the object, although we could call the process weighing something, but we do refer to it as the mass, which again is independent of the force of gravity. So let's talk a little bit about temperature scales and some temperature conversions. So there's really three types of temperature scales that we see here in chemistry. And for the most part, we really see two of these three the most often. There is the Fahrenheit scale, where water boils at 212 degrees Fahrenheit and freezes at 32 degrees Fahrenheit. When we do Fahrenheit, it is degrees. Fahrenheit is the symbol. That is usually what we use to like our temperature and things like that. More of a metric system type of unit is Celsius, and water boils at 100 degrees Celsius and 0 degrees Celsius, it freezes. Those are two numbers you should know when that happens, and that is degrees Celsius. The third temperature scale, which used to be called sort of the absolute temperature scale, was later renamed for our friend Kelvin, and it really is the majority of the time what the temperature needs to be in chemistry. Pretty much, I would say 99% of chemistry formulas and stuff like that that involve temperature, it needs to be in Kelvin. And that is water boils at 373 Kelvin and freezes at 273 Kelvin. A major difference as well is how we write Kelvin. It is just K. There is no degree written with Kelvin, so it's not degrees Kelvin or anything like that. It is just Kelvin by itself. Now, the differences between really where these three temperature scales, water freezes versus where it boils, is really where we get our conversions to use. And for Fahrenheit, there's about 180-degree difference. For Celsius, there's about 100-degree difference, and also about 100-unit difference there for Kelvin. And those really do give us sort of our conversions to go between them. I would say, again, Celsius and Kelvin, we see a lot, probably outside of chapter 2, not going to see too much of Fahrenheit. And as we'll talk about here in just a second, the conversion between those two are really the ones that we do a lot. Most of the time, I would say you're going to take it from Celsius to Kelvin. It's a super common conversion that you have to do in chemistry. So let's talk a little bit how to do those conversions. First off, to convert between Kelvin and Celsius, you take the temperature in Celsius, you add a 273 to it, and it will give you the temperature in Kelvin. The real number is 273.15. Most of the time, people just use 273 because the 0.15 gets rounded off a lot. If you like the 0.15, you could keep it. It don't really matter to me. But again, most people will just roll with the 273. But if you do see 273.15, that really is the proper conversion number there to use. That also means that if you do have the temperature in Kelvin and you want Celsius, you would subtract the 273 to the other side, and that would give you the temperature in Celsius, would be our temperature in Kelvin minus 273. So if you need to go the other way, you're going to subtract 273. You definitely need to know that one is one we use, like I said, a lot here in chemistry. A couple others that we really don't use all that too much outside of chapter 2 is going from Celsius to Fahrenheit, and that would be here. The temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus a 32. And if we wanted to go to calculate Celsius from Fahrenheit, we would subtract the 32 to the other side, divide by the 1.8, and that gives us the temperature in Celsius is equal to temperature in Fahrenheit minus 32.8. Now that 1.8 number is really based off of, as I mentioned, sort of the difference between freezing and boiling of water. Maybe learned it a different way. Also 9/5. It's the same thing. If you take 9 divided by 5, you get 1.8. So if you learn that, it's the same idea there. The Fahrenheit would be 9/5 times the temperature in Celsius plus the 32. Once again, the top there, Celsius to Kelvin, probably 98% of the time, that's what you're going to be doing. A couple of percent of the time, probably going the opposite way there, taking Kelvin back to Celsius. But it's a really, really important one. So you do need to know these three formulas. Once again, they will not be provided for you. And again, probably outside of chapter 2, the top one is really the one. Make sure that you focus in on. Any questions on that? Now, there is a sort of a rule that we follow when we're doing, frankly, just temperature conversion. So we're doing nothing more than taking a temperature value from one unit to the next. The rule that we follow in terms of sort of giving it to the right number of significant figures or digits is we take the conversion and we convert the temperature value to make it look like the original unit. So what that means is if you were taking something from degrees Celsius to Fahrenheit and your degrees Celsius went to the first decimal place, when you would convert it, it would also go to the first decimal place. If you were going from any of these guys and it was a whole number, you would convert it to a whole number. So we really don't in most cases follow really strict significant figure rules when you're dealing with strictly just temperature conversion. And that's because there's a lot of variations that could happen. For example, I use 1.80. Some people use 1.8. Some people use 9/5. So there's a lot of variations how people could do some of these conversions. So the general rule is if you're doing a temperature conversion from one unit to the next, whatever the original number looked like, it was a whole number, went to 2 decimal places, went to 1 decimal place. When you do the conversion, you should take it to the exact same number of places. Any questions on that? Yeah. So why don't you take a couple minutes here and try these here. We're gonna do a few conversions. So first one, we're going to convert to Kelvin, then next one Fahrenheit, and lastly here degrees Celsius. Okay, let's take a look and see how we're doing. So the first one here, got temperatures 28.5 degrees Celsius. We want to convert it to Kelvin. So that's going to be temperature in Kelvin is equal to 273 plus our temperature in Celsius. So we'll take our 273. You want to use the 273.15, you can, but most people just use 273. And if we do that there, we do get an answer of 301.5. Again, this would be Kelvin, no degree unit there, just 301.5. Now, in terms of what we were talking about earlier, our original temperature unit went to the first decimal place. So when we did the conversion, we kept it to the first decimal place here. Any questions on that one there? Looking at the next one, we have our temperature at 41 degrees Celsius. What is it in Fahrenheit? So this is going from Celsius to Fahrenheit. So as we saw on the previous page there, our temperature in Fahrenheit will equal 1.8 temperature in Celsius plus a 32. So put in our numbers in 1.8 are 41 plus a 32, and that will give us 105.8 degrees Fahrenheit. Now, when we look at our original number here, though, it is a whole number, which means we do want to round this to 106, which would take us to our nearest whole number there, rounding up, because that 8 is obviously above 5. Any questions on that there? Lastly here, we got some pork that's been cooked to 160. What is that in Celsius? So our temperature in Celsius equals the temperature in Fahrenheit minus 32 divided by 1.8. Putting in our numbers, 160 minus 32 divided by 1.8. We take 160 minus 32, hit equals, divided by 1.8, hit equals. Hits us a 71.11, whole bunch of ones, degrees Celsius. Should I leave it as that, or what should it end up as? Yeah, again, here looking at our original number, it is a whole number. So we would take this to 71 degrees Celsius. Any questions on any of those three there? So once again, what we're talking about here in terms of sort of giving our final answer is really just specific for temperature to temperature conversions. There's obviously other rules we'll talk about when we do other types of calculations. Any questions? Once again, you do need to know those. They will not be provided for you. So if we look at this, the type of measurements, also really important. You know, when you do take measurements, to understand, you know, what you are looking at. Sometimes very common people take measurements. For example, they go, I got 50 milliliters, and that's my mass. And obviously liters is a volume, not a mass. So it's important to recognize those things. So Kelvin, as we saw, is a unit of temperature, right? Liters is a unit that represents volume. Meters is a unit that represents length. And lastly, kilograms is a unit that represents mass. So when you say you got 20 kilograms of something, that is not the volume. Yeah, so make sure that you understand obviously what those units represent in terms of the type of measurement that is being made. Any questions on any of those there? All right, so I think we just did that. Now, this is a good time to talk about sort of difference between a couple of types of sort of observations and measurements, qualitative versus quantitative. When we talk about something that is qualitative, what that means is usually you're just given general observations about something. You know, maybe it's pink, it's got polka dots, you know, it's on fire, whatever it may be. While quantitative measurements are basically what are referred to as measurements. So when we take measurements, when we record values, those are typically quantitative. They comprise of numbers, units, and some type of measurement that has been done. So a lot of times though, when we do any type of experiment, we sometimes want to really record both of these types of measurements and observations. You generally want to record, you know, anything that you see, any type of color change and, you know, change to the maybe state of a substance or something like that. And you definitely want to make sure that when you do take measurements, that you record it to the proper number of digits. We'll talk about how to do that. And obviously the proper units. So quantitative involves measurements, qualitative more general observations about these substance that you may be looking at. Now, when we do deal with numbers, sometimes we deal with really, really large numbers like that number there, Avogadro's number, like 6022 and a lot of zeros. The mass there of a hydrogen atom, a lot of zeros and like 1.166. Most likely, if you kept those numbers, trying to do some type of calculation, you're probably going to lose a 0 or 2 along the way. So what we do a lot of times is we do write numbers sometimes in what's referred to as scientific notation. It's a way to sort of handle really large numbers, really small numbers. Scientific notation, as we will see, has a general formula of n times 10 to the n. This is a number between 1 and 10. So not 10 and above, not below 1. It needs to be a number between 1 and 10. And this n up here is either a positive or negative number, depending on which way you got to move to basically get yourself a number between 1 and 10. You know, so for example, if we had 325, we would assume the decimal point would be here. We would go one place to the left, two places to the left. That gives us 3.25 times 10 to the 2. We move the decimal place to the left there. We end up with a positive exponent. Our way to remember it is a large number should have a positive exponent. If I only move the decimal point one place to the left, I would be at 32.5, which is clearly not a number between 1 and 10. So that is why we had to go even further. If you have 0.00123, we would go here, one place, two places, and three places gives us a number of 1.23 times 10 to the minus 3. Again, I moved it 3 places, and negative number here because it's a small number is a way to remember it. So small numbers have negative exponents, and obviously positive numbers are more larger numbers in that case. Any questions on that there? Now, you do need to write things. You don't have to, let me say this properly. When you do write some number in scientific notation, it does need to be written properly. Again, a number between 1 and 10. You don't always have to give your answer in scientific notation for me. Some teachers make you, but you don't have to do that for me. But there may be some cases where the only way to get the proper number of significant figures is to write a number in scientific notation. So sometimes you may be forced to do it because it's the only way to get proper number of significant figures. With that being said, we'll talk a little bit more about this in a second, but when we do write a number in scientific notation, all the numbers that come before the times 10 part are significant. So always when we do that, any number here are significant. Yeah. We're going to talk about actually that right now, how to use your calculator properly and actually punch it in. Being able to write it in scientific notation is really important. I guess probably the better way of saying it is I would say most people do not know how to properly punch that into your calculator correctly. So why don't we talk about how I'm doing that? We'll talk about how to do it with our calculator, because that's probably how we're going to do it most of the time, not with our head and kind of adding or dividing and stuff like that. So let's say we had some numbers that are in scientific notation. And let's talk a little bit about your calculator. Every scientific calculator you have should actually have an exponent button. An exponent button is usually the button that's marked EE. It is the button that's sometimes marked EXP. And if you have some of the newer calculators, you may actually have a button that is times 10 to the n or something like that. So if you do, we will talk about you in just a second. But if you have these two buttons here, we'll talk about how to use those properly. So let's say we wanted to put into our calculator a number like we had there a second ago, 1.25 times maybe 10 to the minus 3. So the first thing that you would want to do is go 1.25. You actually would want to hit your exponent button. So either your EE button, either your EXP button. You do not hit the multiplication button. Do not hit shift log or anything like that. You just hit that button. When you do that on most people's calculators, it will either show one of two things, 1.25 and an E, or it may go 1.25 and maybe pop up a couple of zeros up on top, or say times 10 and a couple of zeros up on top. When you hit that exponent button, that represents, when you hit this button, that represents this part of the number, which means you do not need to hit the multiplication button. You do not need to do anything other than just basically hit that button. So what would be left at that point to put in there would be our negative. Now, most calculators actually have a negative button. Looks like this. Looks like this. It is not the subtract button. Yeah. So you would hit your negative button because it's a negative exponent. That will put a negative there. That will probably put a negative right about. And you would just put 3. And that would put 3. And that would make that basically into a 3. So that is the proper way to actually punch it into your calculator. If you again use like the second button, the shift button, and like the log button, the 10 to the x, or you hit the multiplication button, you will be wrong. Yeah. And you usually will know you're wrong because you'll get an answer where the front part of the number looks okay, but the exponent part's off by like 1 or something like that. And that's usually the way that you're punching it in. Now, if you have kind of the newer calculators, or some of the newer calculators, I guess they're not new anymore, they've been out for a while, but they're usually like two-tone. They got like maybe some blue or green and then like white in the middle, kind of a two-tone type calculator that has this button. In order to usually get the right answer, you have to do one extra step, which is you actually have to use your parentheses. And usually if you have this button, you also have like a little dial on your calculator. It looks something like that. So if you have something like that, usually what you need to do is you actually need to open a parentheses first. You then need to hit 1.25. You then hit your times 10 to the n button. That will most likely on your calculator put something like this. And then you'll have your little cursor sort of blinking right about there. You then would hit your negative button and 3. And what it'll end up doing when you do that is you'll look at something like this. And then you will have your little cursor blinking to the right of 3. You then usually need to hit this button there. And when you do, it will bring this back down and you could close the parentheses. So if you have that button, you got a little extra work if you want to punch it into scientific notation correctly. You got to lay up some parentheses around it. You usually have to do this. I've seen a lot of calculators where if you don't hit that button, you'll do this and you go to close the parentheses and it'll make like a little small parentheses up on top, and then you'll get like an error or something like that. So you got to kind of have to hit that to bring it down to do it. So those are that's the proper way to punch it into your calculator, which in some cases is more important than knowing how to write it. It's actually being able to punch it in. Most of the time, that is how you'll probably use some of these scientific notation buttons. Any questions on those other buttons? At no time should you use, again, the multiplication button unless you're actually, and nor should you ever use the log button to do scientific notation. You're definitely doing incorrectly if you are using those buttons. Why don't we try a couple here just to make sure everybody knows how to use your calculator. 5 times 10 to the minus 3. And let's divide it by 2.5 times 10 to the 20. And let's do 3.2 times 10 to the minus 8 times 1.2 times 10 to the, and we'll do 16. All right. So see what you get here. I'll do it too, since I just made it up. So hopefully we'll all get the same answer. Okay, let's take a look, see how you're doing. So again, you want to make sure you use your exponent button. So if I were to punch this in, I would go 1.25. I would hit my exponent button. Obviously, if you have the other one, you need to put parentheses. It's -3, so I would hit my negative button and 3. I then would hit my divide button. 2.5, once again, exponent button. This is a positive exponent, so I could just put 20 at this point, then hit equals. And if you do all that good stuff there, you end up with about 5.0 times 10 to the minus 24, or on your calculator, it may just say 5 times 10 to the minus 24. Any questions on that one? Now, another very common mistake that people make is when they get something on their display, it may look like this, or 5e, and they just write the 5 part. So remember that you need to make sure you include the times 10 part in your answer. And when you are writing it in scientific notation, this would be correct scientific notation. If you wrote the answer like this is not correct scientific notation. We don't use that E when we're writing it out as an answer. It needs to be times 10 to the minus 24. Any questions on that? All right, looking at the bottom one here. 3.2, once again, going to hit my exponent button, going to hit my negative button and 8. And again, that would give you something that looks probably like this on your calculator, or this. Going to hit the multiplication button because I'm multiplying, and then enter this number in scientific notation, 1.2 with the exponent button. And again, this is a positive exponent, so I'll hit that. So it'll look something like this probably on your calculator, depending on your calculator, which one you might have. And again, obviously going to hit equals at this point, and we will end up with 3.2 exponent -8 times 1.2 exponent 16. Going to give me 3, 8, 4, 1, 2, 3, 4, 5, 6. And again, we could put this in scientific notation by going 1, 2, 3, 4, 5, 6, 7, 8. and give us something like 3.8 times 10 to the 8. Again, your calculator may not give it to you in scientific notation unless you have it set up that way. Yes. It doesn't. So in this case, you might want to do it because a lot of zeros, but as long as you have the proper number of sig figs. By the way, I did round these answers to the proper number of sig figs. We'll talk about how come I dropped off a number and stuff like that a little bit down the road here. But it doesn't matter. You don't have to, like I said, always give your answer in scientific notation. But there may be a reason that the only way to give the right answer is to use scientific notation. Clearly, if the answer says use scientific notation or the question says use it, make sure that you do use it. Any questions how to properly punch that into your calculator? If you still are having trouble, again, like I said, most of the time, this part of the number will be good, but that part will be off a little bit. Just come see me. We'll find your exponent button if you're not sure where it's at still or how to use it. I'll be happy to show it to you. So take a look at a couple of these guys here, converting some numbers into scientific notation. Once again, we would need to move 1 and 2 places over to get us 5.68762 times 10 to the 2. Significant figure reasons is why we keep all those numbers. We would go 1, 2, 3, 4, 5, 6 places that way. And that gives us 7.72 times 10 to the minus 6. There's no decimal point written, but we do assume it's here. So this would be 1, 2, 3, and 4 places. Gives us a number between 1 and 10, which is, again, what we're shooting for there. And that would be 1.25 times 10 to the 4. And lastly, coming this way, 1 place gives us 1.35 times 10 to the minus 1. Again, as you can see, bigger numbers above 1, positive exponents, smaller numbers, negative exponents. That's a good way to remember it. Yeah. Any questions on how to write scientific notation, punch it into your calculator, which I think in our case is actually a little bit more important in some cases. Any questions on any of that? Okay. And again, if you're still not sure, just come see me with your calculator and we'll figure it out. We'll skip that one. So what we're going to talk about now is actually taking measurements and knowing how far we should take a measurement. And when we do take measurements, regardless of what type of measurement it is, there's always going to be some degree of uncertainty in the measurement. And the degree of uncertainty really will lie with the type of equipment that you're using. So for example, if we look at something here, if we look at, say, a nice ruler, we'll say these are centimeters, and we wanted to measure, say, this little arrow here. When we look at, say, something like a ruler or any piece of equipment, what we always want to do is make sure that we look at the scale. And there's usually 2 types of measurements, markings. There's usually sort of a larger marking and sort of a smaller marking. And when we look at the larger markings here, we could see that it is 1 centimeter is basically the larger markings. And if we count between 1 centimeter and 2 centimeters here, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings between the 1 and the 2. That means that each of the smaller markings here represent how much? If there's 10 markings between 1 centimeter. Each one represents 0.1 centimeters. This would be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then 2. So the larger markings here represent 1 centimeter, smaller markings represents 0.1 centimeters. So whenever you take a measurement, regardless of the piece of equipment, there should really always be numbers where no matter who takes a look at it, everybody should agree. There's kind of where sometimes referred to as certain numbers. So no matter who takes a look at this, hopefully, everybody should agree it is at least 1.4, not quite 1.5, but it's at least 1.4. So we would want to record 1.4. These are what are referred to as our certain numbers. Now, when we look at that arrow, again, we can see that it is not quite 1.4 exactly, not quite 1.5. It's somewhere in between. And that is where the uncertainty is. That's where the estimation is going to come into play. I may look at that and go, I think it's like perfectly kind of between the two numbers. So I will record that as a 5. Somebody else may look at it and go, I think it's a little closer. Maybe it's a 6, maybe it's a 7, maybe it's a little less, maybe it's a 3, maybe it's a 4. Yes, sir. Yeah. Yeah, we're going to talk about that in just a second. Yeah. So this 5 here would be what is referred to as the first uncertain number. And sometimes people call it the estimated number. And we would record, obviously, the units here, which would be centimeters. And this would be the proper way to record this measurement. When you take a measurement, you should always record all the certain numbers plus the first uncertain number. And actually, when you do that, when you look at a measurement and when you record all the certain numbers plus that first uncertain number, that really is what significant figures are. That is really what significant figures are, which means this measurement right here would have how many significant figures? It would have 3 significant figures. Now, to answer sort of your questions, sometimes what people look at and sometimes what people report with their measurements is sometimes the degree of uncertainty for that particular piece of equipment. And the way that you can basically figure out the uncertainty in a equipment is to take the smallest markings, which in this particular case is 0.1 centimeters, and divide it by 2. And when we take 0.1 divided by 2, we get 0.05 centimeters. And that's sort of the plus or minus, if you will, and sometimes how people sometimes will report this value. They will report 1.45 centimeters plus or minus 0.05 centimeters. Basically means we take the reading to the second decimal place. Is basically what that will tell you as to how far you could take it, which is the tolerance basically of the equipment and stuff like that. Question on that. Personally, for me, I don't really need you unless the instructions say to do so to include that. I'm good with just the measurement, but as you go on, there are other instructors that will want you to sort of record that with your measurements and stuff like that. Yeah. Any measurements that you take, you want to record all the certain numbers plus that very first uncertain number. And if you're really not sure, the kind of usefulness of this part right here is if you're really not sure how far you should take the reading, you could just figure out what the smallest markings are divided by 2, and that's how far you should take the reading and stuff like that. In general, most people will consider a measurement like this, that where we have the 5, that's like plus or minus 1, right? So maybe somewhere in that ballpark is sort of where the maybe real value is and that uncertainty value. Any questions on that there? Now, it does depend on the piece of equipment that you're using. You may have something like this, for example. Get this here. And we'll say this is a graduated cylinder. Probably why I failed art 5 times. It's okay. All right, we'll try this here maybe. Now, when we take a volume reading, what we typically will see, and sort of to exaggerate it, is a curvature of a liquid in a glass container. And that's what's known as the meniscus when you're dealing with a liquid in a glass container. And usually what we want to read is from the bottom of the meniscus. And that is because what is actually happening here is the solution is actually more attracted to the walls of the container. So what happens is the side of the liquid starts rising up the container because there's actually more of attraction to the container than itself. Creates this sort of meniscus that occurs, which means if you didn't have that attraction, those guys wouldn't climb up the sides. And this is actually where the volume is in that particular container. So you should always try to look for the meniscus, sort of the curvature of the liquid. Always want to read from the bottom of the meniscus, unless it's something like mercury, which actually goes the opposite way, it goes upward, the circle, but most of the time it's going to be kind of like a U. So if we look at this guy here, we have 10 and we have 20. Our large here is how much? 1 milliliter, right? And our large markings is because, I'm sorry, our big markings is 10 milliliters, sorry, between 10 and 20. Our smaller markings here, if we look, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So once again, we have 10 markings between 10 milliliters, which means each of the smaller markings represent 1 milliliter in this case, right? This would be 11, that would be 12, 13, 14, 15, 16, 17, 18, 19. So in this particular case, if we were to take our reading from the bottom of the meniscus, which is right about there, everybody should agree that it is at least 14. Once again, we're not exactly at 14, not at 15. So this is where the estimation is. And maybe you don't feel that really is halfway there. Maybe you feel it's a little less than half. So maybe you mark 14.4 milliliters. This would be our certain numbers. This would be our first uncertain number. And that means that this particular case, we have how many significant figures in this answer? This would also have 3 significant figures. You wouldn't necessarily divide 0.4. So what you would divide is the smallest markings to look at the uncertainty. So we take the smallest marking, which would be 1 milliliter, divided by 2 gives us 0.5 milliliters, which means technically speaking, plus or minus 0.5 milliliters. So the uncertainty in this apparatus is basically the first decimal place, which is where we took it. Yeah, let's go our reading. Question on that. Now, in most cases, you typically could take the reading to one more place to the right of the smallest marking. So the smallest marking is 1 milliliter. We could go one more place to the right, and that is what we did here. If we look at we go here, the smallest marking was 0.1. We went one more place to the right, which took us to the second decimal place. So typically speaking, you could go one more place to the right of the smallest marking and you'll be in good shape in most cases. But again, not all cases, because you really do have to look at the scale. Let's say I had this. Milliliters. Now our large marking, right, between the two large markings is 10 and 20, which is still 10 milliliters. When I look at this particular case, I have 1 marking, 2 markings, 3 markings, 4 markings, and 5 markings. So I have 5 markings, which means my small guys represent how much in this case? Each of the smallest markings should represent, they represent 2 milliliters. Yeah, 10 divided by 5 is 2, yeah. Gives you 12 here, right? 14, 16, and 17. Not a 17, 18 would be a better number there. And if I had, say, a volume right about there, very badly strike draw. What should I record in this case? Yeah, between 14 and 16, the best you could do on this scale is 15, right? So 15 milliliters would be what you would record. That would mean this has how many significant figures? It has 2 sig figs, right? The uncertain number is which number? It is the 5 is the uncertain number, yeah. Because it could be as big as 16, it could be as low as 14, but there's no good way on this scale to know where 14 stops, right? And 15 begins before you get to 16. There's just not enough room to figure out, you know, where kind of one starts, one ends, and that type of stuff. So in this case, this would have 2 significant figures. Again, if we took this 2 milliliters divided by 2, 1 milliliter is our tolerance, right? Our uncertainty in this equipment, and it would be 15 milliliters plus or minus 1 milliliter, right? I know equals, but 1 milliliter. Question on that there? Yeah. You do. So you should always keep track of the significant figures and report things to the proper number of significant figures, because when you take measurements, your measurement is only as good as your crappiest measurement. So the one with the least number of significant figures is usually the worst measurement. So your overall measurement and thus your overall calculation is only as good as your worst one. So if you have no idea which one's your worst one, you have no idea to what to give the final answer would be and how good or bad that answer would be. Yeah. Other questions? Now, another very important thing is, let's go back to this guy, I think. Now, what happens if we had our arrow here and it was something like dead on that 1.3? What should I record? Should I record 1.3 centimeters, 1.30 centimeters, 1.3000 centimeters? Because I feel like if I add more numbers, it might be better. Is there a difference between all those measurements in terms of, you know, is it right or wrong? The answer is there is a big difference between each of those. So let's take a look at each of them here. If I record 1.3 centimeters, right? That is how many significant figures? That would be 2 sig figs, right? Which means the uncertain number would be which number? Would be the 3. So really what you're saying in this case is I think it's 1.3, but maybe it's 1.4, maybe it's 1.2. If I look at where I'm at, you could clearly see I'm kind of nowhere near any of those things, right? I'll get rid of this. This is like way too many zeros. We'll take a look at this number. If I record 1.30 centimeters, how many significant figures would it have? It has 3 significant figures, right? The uncertain number then in this case would be? It would be the 0. Which means that what you're saying is, I think it's 1.30, but maybe it's like 1.31, maybe it's 1.29, which frankly is pretty much what we're looking at on this piece of equipment, right? So because we do have the ability on this piece of equipment that we figured out from here, the uncertainty or the tolerance of it, if you hit directly on a number, you have to keep the 0. Because if you do not keep the 0, you're making your measurement pretty crappy. Yeah, there's a big difference between 1.4 and 1.2 versus like 0.01 and 0.02 type of difference. Yeah. Question? So that is a very good question, and the answer is usually is the right way to say that. So whenever you look at a measurement and you're trying to figure out where the estimated digit is or where the uncertain digit is, it is always the last significant figure, not always the last digit. So whatever digit is the last significant figure is where the uncertainty lies. So for example, talk about that in just a second. Any other questions on that there? All right, so really important when you take measurements like in today's lab, that you look at all the scaling, figure out how far you can take that reading, and always take it to the proper number. So there is a difference also between two terms that are sometimes used, which is accuracy and precision. Accuracy tells us how close we are to the true value, while precision refers to how close a set of numbers. So the classic example is the bullseye. Throw some darts, right? The goal here, right, is to sort of hit the bullseye in the middle. So I throw my darts, I hit there, I hit there. Perhaps I missed the board. Hopefully nobody was standing there. Am I accurate? I would say no, since I completely missed the board, right? Am I precise? I'm not either. Those three shots are kind of nowhere near each other, right? So that's neither accurate nor is it precise. I go, well, friendly, double or nothing, I suppose. Pick up my darts and my pride. And then I throw the darts again. And I go boom, boom, and boom. Am I accurate? I'm not, because I really didn't get anywhere near the bullseye where I'm shooting. Am I precise? I'm precisely not accurate. Yes. It proves a very good point in chemistry and science. You could do something wrong every time the same way, right? And you get the same answer every time because, frankly, you're doing it wrong every single time. But you could be very good at doing it wrong every single time and be very precise in your numbers, but not very accurate in how you're actually doing it. So I go a friendly triple or nothing. That's usually when you should say, no, I don't want to do that because I feel like I'm getting hustled here. And I throw my darts and I go boom, boom, and boom. Am I accurate? Am I precise? Yeah, and that's usually what you're shooting for. Obviously, when you take measurements and do sort of labs, you want to be accurate and you also want to be precise. You want to be accurate in terms of getting the right answer. You also want to be precise in being able to, what's sometimes referred to as being reproducible. Your results need to be reproducible. That's why in science and chemistry, we oftentimes will do experiments where we do like 3 trials or 2 trials or 4 trials, and you repeat the same sort of procedure multiple times to see if you get basically the same outcome. And it was very reproducible. So precision oftentimes will look at sort of the reproducibility. Accuracy will look at obviously how well you did. Any questions on that there? That's pretty much what this guy says. I went with the home drawn dartboard. All right. All right, so let's take a couple of readings here. What should be the proper reading of this? Hopefully nothing moved. All right, so since we're kind of to the end here, let's take a look here together. Big markings here, 2 to 3 is 1 centimeter. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. As you can see, when you start counting, you start for the hash mark to the right of the last biggest marking and kind of count to the next one. So that's 10 markings in between 1 centimeter, which means the smallest markings here represent 0.1 centimeters. Yes. That means that this first marking here would be 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, and 2.7. So for sure, everybody should agree it is at least 2.6. It is clearly not exactly 2.6. It's almost to that 2.7. So I'm thinking we should maybe go with a 9 here, centimeters. And that would be how many significant figures? Be 3. We actually have 2 of them here. So let's see which one's right. We know the smallest marking is 0.1 divided by 2 gives us 0.05 centimeters as our uncertainty in this measurement. So I'm going with D, should be our right answer here. Once again, for me, you don't necessarily have to do the plus or minus 0.05, but some people do it. Let's take a look, one last one here before we call it a day. Looking here, we have 8 and we have 9 to 10. So once again, our large markings going to be 1 centimeter. We have, again, if we count it, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings between them, which means once again here our small markings are going to be 0.1. Just past the 9, which means we should look at something like, for sure it is 9, and it's not exactly 9.1, so it's got to be less than that. So 9.02, once again, with our marking here being 0.05 centimeters. We get that again by doing that. Also tells us how far we should take the reading. 0.05, 2 decimal places. That's how far we should take the reading in that case.